We are doing PHY Physics 156, General Physics 1, Chapter 5 problems, and we're starting with number 3. The horizontal force of 310 newtons is exerted against a ball as it rotates at arm's length uniformly in the horizontal circle of radius that. Calculate the speed of the ball. Okay, so we got some horizontal surface. We got a ball. It's 2.0 kilograms. We have a force pushing it. That's 310 newtons. Horizontal force rotates at arm's length uniformly in a horizontal circle of radius 0.9. Okay, so 0.9 is that. I'm pushing it, rotating like that. Alright, calculate the speed of the ball. So I want to know the speed. Alright, well, a horizontal force is exerted on a ball as it rotates in a uniform circle of that. Okay, so that's not what's happening. Okay, so this ball, 0.9 meters that way, is rotating in a circle like that, and a force is applied here of 310 newtons, and it's 2.0 kilograms. Okay, I think that's the problem that we're working on. Okay, so that's the problem we're working on, and so force is equal to mass v squared over r. This is equation 5-3. So I've got 310 is equal to 2 kilograms times 2 velocity squared divided by 0.9 meters. So my velocity is going to be the square root of 0.9 times 310 divided by 2. And it's going to be 11.8 meters per second squared. Meters per second, not squared. Alright, next problem, number 29. At the surface of a certain planet, G is 12 meters per second squared. A 24-pound brass ball is transported to the planet. What is the mass? So A, the mass stays the same, 24.0 kilograms. B, what is the weight? B, the weight of the ball on the Earth and on this planet. Okay, so the weight on the Earth, 24 times 9.8, the weight on the planet 24 times 12. Okay, so 24 times 9.8, 2 point, bummer. Word floating point. Why am I not being given the right answer? 24 times 9.8. Yeah, that's better. 235, and that's all we got. 235 newtons. 24 times 12. 288 newtons. Okay, that's all there is. There ain't no more. Number 40. You are explaining to a friend why an astronaut feels weightless in a space shuttle, and they respond that they thought gravity was only weaker out there. Convince them that it isn't so by calculating how much weaker the gravity is at 380 kilometers above the Earth. So 380 kilometers above the Earth. And, okay, so we look at 5.6. And we find that gravity is going to be G, the gravitational constant, mass of the Earth, divided by the radius squared of the Earth. Alright, so that's going to be G, which is 6.67 10 to the minus 11. 6.67 times 10 to the minus 11. Mass of the Earth. Mass of the Earth, 598 10 to the 24th. 5.98 times 10 to the 24th kilograms, divided by the radius of the Earth. Radius of the Earth, 6.38 10 to the third. 6.38 10 to the third kilometers. That's really 10 to the 6 meters plus 0.38 times 10 to the 6 meters squared. So gravity at G, the gravitational constant, is 380 kilometers above the Earth, will be 6.67 double E minus 11 times 5.98 double E 24 divided by parentheses 6.38 double E 6 plus 0.38 double E 6 close parentheses squared equals 8.73. 8.73, or is it 37? Nope, 73 meters per second squared. How come does he feel weightless? That's not all that much less than 8.9 meters per second squared. What is going on? Does it ask us that? No, it doesn't. It says, convince them that you're right. Well, you just convinced me that you're wrong. So what's happening is when you're in orbit above the Earth, you're falling as fast as gravity's pulling you, and that's why you're weightless as you rotate around the Earth. It has no idea. It's not the gravity that's actually there. It's just your frame of reference is moving. Okay, where were we? Number 40. Or was that number 40?
That was 40.
Excellent. 45 is next. 45. A space shuttle releases a satellite into a circular orbit 780 kilometers above the Earth. How fast must the shuttle be moving when it releases the shuttle into a circular orbit? Okay, so this is the same chapter that we're in. And how fast must it be going? Okay. Is that okay? So from we have an equation that says V is equal to the square root of G ME divided by R. Alright, so V is equal to 6.67 times 10 to the minus 11 times the mass of the Earth, which I don't remember, but is in your calculator in case you forget it. 9.89 10 to the 24th, 5.89. 5.98 9, 8, 10 to the 24th divided by the radius. So the radius would be radius of the Earth 6.37 10 to the 6. 6.38 times 10 to the 6 plus 0.78 times 10 to the 6 square root of the whole thing. Okay, second function, square root key, 6.67 double E minus 11 times 5.98 double E 24 divided by, open parentheses, 6.38 double E 6 plus 0.78 double E 6, close parentheses again, the button. We'll call it 7,500. 7,500 meters per second. Thinking that we only have two significant digits, which is probably all we have. 45. Yep, all we have. 55. At what rate must a cylinder spacecraft rotate in order to simulate gravity at 0.7 g? Okay, so 0.7 times 9.8 is 0.7 times 9.8, 6.86. 6.86 meters per second squared. And my diameter is 32 meters, meaning my radius is 16 meters. Okay, and we want the answer, and give your answer as the time needed for run revolution. So all we want is the period, okay. Alright, so yeah, I don't think that that's part of there. That's better. Okay, so the equation we want is AR is equal to v squared over r. So that being the case, 6.86 meters per second squared is equal to velocity squared divided by r, which is 16. So the speed I'm going to want is the square root of 16 times 6.86. .5 meters per second. 10.5 meters per second. My circumference is pi d, which is 32 pi, and that's going to be in meters. Okay, so if I take 32 pi and divide it by 10.5 meters per second, I end up with seconds. Okay, so I've got to take 32 times pi divided by 10.5, I end up with 9.6 seconds per revolution. And we wanted the answer to be time needed for one revolution. Okay, so 9.6 seconds per revolution is all I need to do to have the gravity that big. Number 57. Newton's average distance. So distance to Neptune, 4.5, 10 to the minus 9th meters from the sun. Estimate the length of the Newtonian year using the fact that the Earth is distance of the Earth is 1.5 times 10 to the 8, 9, 10, 11 meters. This is 12 meters. And the Earth, the time for the Earth is 365.25 days. Okay, so I gleaned everything I need there. Back to Kepler's law in section 5-8. And we see that T1 over T2 squared is equal to distance 1 over distance 2 cubed. Alright, so 365.25 is to T2 as 1.5 times 10 to the 11th is to 4.5 times 10 to the 12th cubed. So T2 is the square root of 365.25 squared times 4.5 times 10 to the 12th cubed divided by 1.5 times 10 to the 11th cubed. Alright, well, square root of 365.25 squared times 4.5 double E 12 cubed divided by 1.5 double E 11 cubed. And we have 60,000 days.
Did you cube it?
Huh?
Did you cube it?
I don't know what I did wrong. But that ain't right, I know that. Way to go, calculator. Alright, so we're going to go 365.25 squared times 4.5 double E 12 cubed divided by 1.5 double E 11 cubed equals square root of the answer. 60,000 days. Oh, maybe that's right. Yeah, that's 60,000 days. Okay, 60,000, 16 days. Well, we'd do it in years probably. Divided by 365.35. So that's only 164 years. That's reasonable. 164 years. Alright. Doesn't get around there in your lifetime. Well, maybe your lifetime, but not mine. That was 55. No, that's
57.
That's 57. So we're doing 58 next. The asteroid, though only a few hundred meters long, orbits the Earth like the planets. Its period is 410 days. What is the mean distance from the Sun? Okay, so the period of the Earth is 365.25, and the distance of the Earth is 700. Come on, looking it up. 1.5 times 10 to the 9th. 1.5 times 10 to the 11th. 1.5 times 10 to the 11th meters. Alright, well, so 410 divided by 36.25 squared is equal to distance to the meteor divided by 1.5 times 10 to the 11th cubed. Alright, so distance, mean distance of the meteorite. Alright. Cube root of 3. Cube root of parentheses 410 squared divided by 365.25 squared times 1.5 double E 11 cubed close parentheses equals so I got 1.62 times 10 to the 11th meters. That seems okay. That was 57. Now we're going to 58. We just did 58. So it looks like we do 69.
So the final answer for 58 was
1 point something. 1.6 times 10 to the 11th meters.
okay.
If you wanted to write it in kilometers, subtract 3, 1.62 times 10 to the 8th kilometers. You could write it that way too. Or you could write it as 162 times 10 to the 6th kilometers. You could write it that way too. All those are the same.
Okay.
I don't know why you want to write it any different, but that's all right. 69. A device for training astronauts and jet fighter pilots is designed to move the trainee in a horizontal circle of radius 11.0 meters. If the force is 7.54 times gravity, 9.8. 7.54 times 9.8. 73.9 meters per second squared. Her own weight. How fast is she resolving? Express your answer in meters per second and revolutions per second. Alright, so we already did this problem. What was it? It was AR is equal to V squared over R. That was the equation we used. So 73.9 is equal to V squared over 11. V is equal to the square root of 11 times 73.9. So square root 11 times 73.9, 28.5 meters per second. The circumference of this is 11 pi. So my period would be 11 pi divided by 28.5 meters per second. 11 times pi divided by 80, 24.5. 1.21 seconds per revolution. Okay, so we want our answer in revolutions per second in meters per second. Okay, so we already got our meters per second answer there. That's there. We want this in revolutions per second. So 1 over 1.2, 0.825 revolutions per second. Okay, and that ends chapter 5 problem.